Now in the final video of this series, we have human participants and run an experiment in a large Markov decision problem. And we want to understand how novelty, surprise, and reward interact. And then we are going to compare this with a hybrid model of novelty, surprise, and reward. So what does the experiment look like? Humans see images. For example, here at time t, they see the image of a coffee cup. After about 1 second, little buttons appear on the screen, and these are the action buttons. After a response time chosen by the participant chooses one of the actions. For example, here the participant has chosen action number 4. And then this action leads the participant to the next stage. After some time, there will again action buttons that show up. The participant will choose an action and so forth until finally, after many steps, the participant arrives at the goal, and that's the end of the episode. Now, these transitions between states and actions are controlled by a transition graph that is unknown to the participant, but which I can show you. So, for example, the coffee cup might be state 3. The participant has chosen action 4, and this action 4 leads the participant to the light bulb. If he had chosen action 3, he would have stayed. If he had chosen action 2 or 1, he would have gone down to one of the trap states. The only goal is at the very end, and this has a certain reward value that is, say, +1. All the other rewards are 0. So, suppose the participant starts in state number 1. It will search around. There are always 2 actions that lead down to the trap states. So the participant will spend a lot of time in the trap states. He will circle around until finally the participant will indeed reach the goal. How long does it take? Well, the participants need on average about 150 actions in episode 1. 150 actions on average until they find the goal. So here's the graph, episode 1, and 100 actions, 150 actions. Some participants take 220 actions. It's a wide range, but it's only in the range of 100 to 150 actions. Now that's amazing, because doing a random search on this graph would give an average time to find the goal of more than 10,000 state action pairs. So participants have some sort of strategy to find the goal. Now in episode 2, the number of actions is very small. It's in the range of 10, 8 type actions, which basically means participants go straight to the goal. Maybe they do one little detour, they are wrong once, but they know how to find the goal. And the same is true in the next episodes. Now we play a little trick in this environment. After episode 5, we switch the assignment of images to states. In fact, the cup image that I said was previously state number 3 is still state number 3, but state number 3 is now at the position of state number 7, whereas the old state number 7 is now at the position of state number 3. So, if you play the game, you will be confused, you will be surprised. Nevertheless, participants only take about 100 actions to understand the new configuration and go back in the first episode after the switch to the goal. And then again, they are no longer confused. They go more or less straight to the goal. So in episodes 5 and 6, participants rapidly relearn, they readjust to the new configuration. Several questions arise. Is surprise necessary to explain this relearning effect? Other questions. Are the human participants basically using a model-based or rather a model-free strategy? And then we saw there is this rapid exploration in episode number 1. Is novelty a good explanation of these results, of this rapid exploration of the environment? Let us try to answer these questions using a model. So this is the model that I discussed before. It takes states and rewards as inputs. It calculates the momentary novelty. So we have a triplet. Then it goes into a model-based branch with model-based Q values for reward and novelty. It also has a model-free branch with model-free Q values for reward and novelty. And then it's combined in a hybrid policy. So it's a rich model. Question: are all components important to explain the human behavior? And this is what we try to do here. So we have here again the model with all the components. Then we can turn off novelty. That means we only use reward-based Q values and forget the novelty-based Q values. Or we can turn off surprise. That means we no longer modulate the learning rate by surprise. Now let's see what happens if we turn off surprise. The full model has surprise, novelty, and reward. It's called Cerner. Surprise, novelty, and reward. And this is by far the best model. Now, if I take this model and just turn off the modulation by surprise, I still have a hybrid model that has model-based and model-free branches. It has novelty, N stands for novelty, but it's just not as good. This is how likely it is, the expected model posterior probability or exceedance probability, how likely it is that a given model is the better explanation. And this is by far the better explanation, to use the model with surprise. Now, we can also say, let's turn off the model-free, the model-based part, which leaves us model-free. Model-free are these components. And then we can have model-free with surprise and novelty, or model-free just with novelty, or model-free but with optimistic initialization. Or we can turn off model-free, and then we have the model-based component. Model-based with surprise, model-based just with novelty, or model-based with surprise and optimistic initialization. And we see that model-based never wins. If there is a second possibility, then it would be this one here, model-free with surprise and novelty. So the clear winner is the full model, this model here with surprise, novelty, and reward. And this Cerner model combines model-based and model-free. If you want to get rid of a component, let's get rid of model-based. So, finding number 4 is rapid relearning needs surprise. This is this huge difference between a version with all components except surprise. We need the surprise for the rapid relearning. So the surprise modulates the learning rate, and this is the surprise, that's the base factor surprise, that's the learning rate of the model-free component, and it has this standard monotonic part. And when we enter the new environment in episode 6, after episode 5, there are strong predictions with a certain action. I will end in state 3, but instead I end in state number 7. Therefore, I'm surprised. And this high surprise value here, that gives a high update of the learning rate there for a high update of the model-free estimation of Q values. So the model-free dominates human behavior in the presence of surprise. We need surprise. We can compare the component of model-based versus model-free, and we see that the model-free is much more important. Here is the relative importance of model-free versus model-based. So here, model-free is more than 4 times more important. Model-free is more than 10 times more important than model-based. Even in episode number 1, the very first episode, model-free is more important to explain human behavior than model-based. Surprise is used to modulate the learning rate. Surprise is against expectation. Hence, surprise needs a model of the environment. It needs a world model. To calculate surprise, you need the transition matrix from S to S prime under action A. So, surprise needs this transition matrix. This transition matrix would, in principle, for an algorithm, enable to plan ahead. It would enable to do update of Q values in the background, but that's not how humans do it. This world model, this transition matrix, is not used to do planning. It's just used to extract surprise. So let's compare. So we have reward-based learning with a reward prediction error. We have surprise-based learning driven by surprise. Reward prediction error is defined as a TD error. Surprise is the base factor surprise that we have seen. We know how to stimulate reward or reward prediction error. It's stimulated by chocolate, by money, by praise, and this modulates the learning rate. We know how to stimulate surprise. It's stimulated by observations that are not consistent with the momentary model of the environment. An observation that violates expectations. And then these violations give surprise, and surprise modulates the learning rate. So this is a current field of research in reinforcement learning, exploration, or more generally, intrinsically motivated reinforcement learning algorithms. And again, as we have seen here in this last video, we have an interaction between observation of how humans are solving a task and algorithms. Exploration is a big topic. Exploration is in humans not done with some type of exploration bonus, but really separate modules. There's a module for novelty-based Q values, and then you can switch the importance of novelty Q values versus reward-based Q values depending on the demands. Exploration is driven by novelty. Humans use novelty to support exploration, and surprise is used by humans to detect changes and adapt the learning rate. You crank up the learning rate when you have discovered a surprising observation that's not consistent with your current model of the environment. And this model of the world is not really used for model-based planning in the background, but it's mainly used to detect changes and adapt the learning rate. And that means it's used to generate the feeling of surprise.